All right, we're live. I'm Justin Meyer, and with me, as always, or hopefully as always, is Alexis Abril, Bitovi's other trainer. Today, we're going to be talking about data types, operators, and primitives. I'm going to get started and share my screen. So give me 1 second to do that. And Alexis is going to be monitoring the JS training Gitter room, so make sure you're asking questions there. And Alexis is going to let me know if he can see my screen when I do this. Can you see it? Alexis?
Sure can.
Okay. Awesome. All right, let me know make sure that I'm coming through okay, and I don't have to switch my internet connection to do this. But I'll get started. Yeah, so welcome back to Bitovi's JavaScript training, where our goal is to take, kind of intermediate developers, people who have done a little bit of JavaScript work here and there, but to get them so that they know how to build and architect the most complex JavaScript applications. I am Justin Meyer, CEO of Bitovi, and with me is Alexis Abril, Bitovi's other trainer. The format for these is going to be a lecture, sometimes exercises, not today. Make sure you're asking questions in Gitter, and our Gitter room is a Bitovi JS training, and we have a training repository where we're putting up these slides. And today is brought to you by Bitovi. Bitovi is a JavaScript consulting company. We build amazing applications inside and out. If you like these trainings, let your friends know, or your employers know that you would like a full training, and we can fly out and teach your team how to do what we do. So as I said, today we're talking about data types, operators, and primitives. What that means is every language has data types. These are JavaScript's data types. Data types you can think of are the chemistry. They're like the elements in a periodic table that you use to combine to create your application, to create life, if you will. JavaScript has two main sets of data types. Those are the primitive types, which are undefined, null, true, strings, numbers. Those are the primitive types. These are passed by value instead of passed by reference, which we'll talk about what that means. And there are the object types of JavaScript supports, which is the object, which is kind of like a hash map, which we'll talk about hash maps at the end of this. There's the array type, the date type, regular expressions, which allow you to parse strings more easily. And then there's a special function type. And functions are just like objects, except that you can call them. So these are JavaScript's data types. So again, the analogy I always use is like the atoms in your chemistry. How those atoms can be rearranged is the operators, right? So JavaScript also has data types and it has operators. This is the physics or the chemistry that allows you to rearrange your data types into your application. So running through this, there's the var keyword, which creates essentially a pointer, which is in some ways like a data type itself. It creates a reference to another data type when it's used in conjunction with the assignment operator. There's the new keyword, which creates kind of a new object in memory that inherits through its prototype chain, can inherit other functionality, which we'll learn how that works in like 2 more weeks. The assignment operator, which sets either a variable to point to another data type or assigns a property to point to another data type. The delete operator, which deletes a which deletes a property reference. You can't use delete to delete a variable reference. You can only use it to delete properties. The member operator, or the dot operator, which reads a property. The index operator, which also reads a property, but that property can be dynamically defined. So here we're passing a string value to read from foo. And then there's the call operator, which reads a function. And there's a dot call operator, which reads a function but had a dot operator before it. Those actually those two things do slightly different things, which we'll talk about when we talk about how this works, the keyword this works in JavaScript. And then finally, JavaScript has a ton of comparison operators. The two most important to understand are equal and triple equal, and we'll go through how those work, I think, in the next lecture or the lecture after that. But what we want to first make sure people understand is how the equal operator works, and how different data types through their properties and or through variables are assembled. So here's a quick example of, I just want to make sure, Alexis, are you everything's still going well? Yeah, you just weren't moving for a second, so I was worried that I wasn't coming through. Okay, so in this example, I'm going to ask a question which seems kind of weird. Why is me.name.first still Justin instead of Alexis? If you look at this code, it can be a little confusing at first. So I create this me object, and it has a nested name object whose first property is Justin. We're going to set the name property, or we're going to create a name variable and then set that to me.name. Right here. So we're also creating a name variable and setting it to me.name, which you would think that, okay, well, name is then is Justin. But then we're going to set name to an object that's first Alexis. Why is me.name.first still Justin, even though we changed what name is? Well, we're gonna talk about that. But first, it's important to understand how variables and pointers and references work in memory. And what I'm about to do is go through how an approximation of what JavaScript does when it sees this code and it runs this code in memory. So we're going to have physical memory on the left, where this is each memory address, and these are the bytes that represent what's going on in physical memory. And on the right, we're going to have a 2D representation of what's going on in the browser. Now, this is the browser. We're going to call these call objects, and we're going to learn a lot more about what call objects are and how they work. Whenever any code is run, it's ran in the global call object, which is often called the window. The window will have references to all of these things. The window, in truth, is a little bit different. Maybe now with the introduction of Node, we could call this global, but the global call object is what everything is running, and this stores all variables that are created within the global call object. So let's talk about how JavaScript breaks this piece of code down. The first thing that's going to happen is JavaScript, after it parses this, is going to see that there's an expression on the right-hand side that needs to be evaluated. Oh, one thing I forgot to mention: our call object's memory address is this little space right here. We'll talk about how that's used in a moment. But the first thing JavaScript does is says, okay, well, I've got an equal sign here, so I need to evaluate what's on the right hand of the expression before I do what's on the left hand of the expression. So it's going to say, okay, there's a string hi being created in memory. So we'll create a little string in our two-dimensional memory space called hi. And then we're going to create the actual string in physical memory over here on the left. So this is just a representation of the same string getting created two different ways. In JavaScript, because type is associated with the actual object and not with the actual value, and not actual with the reference. Whenever a string is created, it uses a memory address to label the type of data that it has, and then it might, in some implementation of string, have the number of characters in the string, followed by the bytes for each character of the string listed in memory. And physical memory address typically has 4 bytes for every physical memory address, so that's why I have H and I. And if I had hello world, I would have HELL and then O space WR, and would only have 4 characters for each memory address. But so you can imagine something like this is added to physical memory, and this is in our 2-dimensional memory. And then the next thing JavaScript does is it's going to do the left-hand side of the expression, which is going to be creating a variable in the current call object. So it's going to create a stir reference in this call object here. So this is kind of a container for all variables, and we're going to represent that in physical memory by having the name of our pointer, of our variable, followed by the memory address of what that variable points to. So right now we've just created a variable in memory, so we've just labeled it, but we haven't actually assigned it yet. That's the next thing that's going to happen, is assignment. So the equal operator is going to run. And what that's going to do is set stir to point to the value high in memory. And what that looks like in physical memory is it's going to actually write the memory address of the data that you're pointing to. So this way, if we needed to look up stir, we could kind of go through the call object. This isn't what happens in reality, but it's an approximation. We could go through the call object, find the value that we're trying to read, go to the next memory address space to then reference the actual data that stir points to. So that's kind of how pointers work a little bit in memory. This is an important thing to understand. So now let's talk about how a little bit more complex of an example might work. So here I'm creating an object in memory. I'm assigning its property text to a string high. I've got my window, and I've got my call object. And let's go through what JavaScript does. So first thing it's going to do is the right hand of the equal expression, and it's going to say, oh, I'm creating an object in memory. So I'm going to represent that object in memory with just a circle. But in physical memory, I'm going to create in a place, I'm going to consume some physical memory. I'm going to put the object's kind of special identifier in the first memory address, and then I'm going to follow that up with the number of properties in that object, and that's it when I start. Then I'm going to do what's on the left-hand side of the equal operator. I'm going to create a variable in memory, and I'm going to create a variable in my call object. And then I'm going to do the assignment. So I'm pointing object at memory address 2001. The next thing we're going to do in memory is create this string high. So we have the high string in memory. And we're going to create that in physical memory, just like we did before. And then we're going to do what's on the left-hand side of the equal operator. And what we first have to do is we have to look up object in memory. So to look up object in memory, well, I'm always going to go to the current call object and look if it has an object property. If it does, I'm going to follow that pointer address number to the actual physical memory, and I'm going to say, oh, I've got an object here. Now I've got that object, and I'm going to do the dot equal operator on it, which is going to set on this object a new property that points at whatever was on the right-hand side of the equal operator. So that you can think of the equal operator is a little bit different than the dot equal operator. So in this case, dot equal, so here, let me step back. I'm going to, in my 2-dimensional memory, all I'm going to do is draw a line from my object called text and point it at the string high. In physical memory, what that's going to do is say, okay, well, now our object has another property, and we're going to call it the text property, and then in the following memory address, we're going to point at the memory address of the string. So this is how when eventually, if it came time to read object.text, you would go to the current call object, find object, then go to that memory address, find text, and then eventually work your way to the string. Okay. So let's talk about a little bit about what delete does then. So here I'm creating object with a nested name object in memory. So whenever, let's see what JavaScript does with this in two-dimensional memory. It's going to create a me variable that points to a object with a name property with a first Justin. And again, JavaScript is really going to do this in kind of you can think of it as in reverse order. First, it's going to create Justin, then it's going to create an object with a first property that points to Justin. Then it's going to create this object with a name property that points to this object, and then it's going to create me that points to that object. And if you guys see, you know, that I use my own name for a lot of these slides, it's not that I'm narcissistic, I'm just not creative. So okay, that's what's set up in memory. And then we're gonna assign the name property to equal me.name. What this is gonna do is create a new variable in memory and point it at me.name. So that's what we have set up in memory. So when we delete, if we call the delete operator to delete me.name, so it's going to delete this property. The delete operator in JavaScript never actually deletes memory. All it does is delete pointer properties on objects. So if I call delete me.name, it's actually not going to delete what me.name points to. Instead, it's just going to remove this name property, right? So that's why name.first can still be Justin. So this brings me to how Typeof works, or a little bit talking about this stuff can hopefully explain a little bit how Typeof works. If you remember a few slides ago, every data type that gets created has this little unique identifier describing, it's really a number, like string might be 3 and object might be 4. It's a little number that identifies what type of data the following bytes represent. That's what Typeof is essentially reading and giving back to you. So that's why when you do Typeof undefined, it's reading that first byte and giving you back undefined. There's a bug in how Typeof is implemented in early versions of JavaScript, which is the reason why Typeof null gives you back object. It was basically a missing curly brace. So this is a bug, but if you read Typeof null, you're always going to get object back, basically because of a bug. But just know that Typeof null is object. But all of the other things that all of the other typeofs give you basically that first identifier back, what it is. The only other one that's a little bit, well, functions are treated a little bit differently, have a different identifier. So that's why you get Typeof function, even though functions act just like objects. So if you do Typeof array, you still get an object back because it's just reading that unique identifier for the type, which is an object, even though it is an array and acts like an array. But to the most primitive low-layer system of how CanJS works, it's an object. So in summary, the things to take away from this lecture is that variables are always stored in a call object. So this is going to be really important when we understand how closures work and how functions work. So whenever you see a variable, you could think of it as there's some kind of container that variable is being put into that contains all the variables. And then the equal operator does one of two things. If you're setting a variable to equal something, well, that points that variable at that something else. And if you are setting dot equal, so if you're setting a property equal to something, that creates a property on whatever object you have and points that property at whatever value you're pointing at. So when we go back to this, we can hopefully understand why setting name equal to first Alexis was not actually changing the value of me.name.first. Again, let's see what's going on with two-dimensional memory space. We're creating this nested object structure here with a first name property surrounded by an object who has a name property that points to that. Finally, the me variable points to the outermost object here, so we set that up in memory. Then we're going to set name to point to the value of me.name. So when you say name equals me.name, it's not actually somehow a pointer pointing at a pointer. So it's not like somehow name is pointing at the value of what this name pointer, well, it is pointing at the value of what name pointer points at, but it's not actually pointing at this pointer itself. So if this pointer changes, name doesn't change. And that's the, and vice versa. They don't like, they're not pointing at the same like memory address number. Instead, they're pointing at the actual value. It's its own pointer. So that's why when we set name now equal to something else, we're just creating that object and then setting name to point to that now. So that's why me.name.first is still going to point at Justin. So,
hey, Justin.
Yeah.
Got a question for you. What is not a number, and why is type of not a number a number?
What is not a number is still, it's very confusing, and I've never actually heard someone answer this really well, and I'm sure you could probably find a quick Google search. Maybe we'll find someone who can articulate this much better. But not a number is still like if you look at its kind of in data type, it's number, but it's not. If you have to, in order to test if it's like is an actual number, like not a number is not equal to equal to not a number. It's very confusing. The way that I think of it is, I think of it as like, what is something divided? What is 0 divided by 0? What you need some reference for things that are like, what is a string divided by 0 or something like that? What you need something for like where, your mathematical algebra just goes haywire and you get a result for that, which is not a number. Now, technically, that is still a number type, but it's not a number. So I think that it's just a way for JavaScript, especially to express these kind of ideas, where you're doing mathematical computations that result with things that can't produce a result. But you need to produce a result for JavaScript, so it produces this not a number value.
I like the mathematical analogy there. If you had 1 divided by 0 and 2 divided by 0, are those things equivalent? And that's why you get things like not a number.
Infinity, you get kind of, I think you get infinity in JavaScript when you do 1 divided by 0.
No, yeah, from a conceptual perspective, like a mathematician would say 1 divided by 0. What would the mathematician outside of JavaScript think? Would those two things be equivalent? So it's giving us giving a label to that.
Yeah, I always see it as like, what's a string divided by 0? Like,
yeah.
What do you do with that? So that's what they say. It's like, okay, here, we're not going to throw an error. Instead, we're going to give you this weird value back. Okay, so we got through here. We're in a bonus, so I'm going to do my best before this is the last thing I'm going to talk about. I'm going to do my best to explain how hash maps work. I didn't create a slide for this, but it's something that I've been recently trying to describe to people. So I'm going to switch my camera. And when I say hash maps, I mean how, and everybody can see that I'm getting painting done right now. Let's see, how do I change my camera again? Okay, all right. Can you see that already, Alexis?
Yep, you're good.
Okay, so let me make sure that this writes okay.
You might want to scoot your hand on the paper to the right a few inches.
Yeah. You mean this way?
Yep.
Or this way?
Yeah, no, the other way. Yeah,
It's gonna be a
and then
little. I
down.
need like a better mount for my camera. It's gonna kind of have to go like this, I think. So, and it might be hard to see, but I'll write it out and then move my hand. So, well, that's ugly. Sorry, I have really bad handwriting, but let me draw it a little bit nicer. So the normal JavaScript object, that is a hash map, right? And hash maps are a very special form of a data type because they have they have very fast insertion and removal for specific values. When I say very fast, I mean if I do something like this, if I create an object, let me do, if I do A equals an object, and I do A dot B equals 1, and I do A dot C equals 2, and I do A dot D equals 3. If I do A dot C, it will give me back the value of A dot C in what's counted as order 1 operation. So it doesn't matter how many properties I'm adding here. Alexis, do you see my camera the right way? Because I think Google is reversing it for me. So when I look at my screen, it's all backwards, but do you see it right?
This looks good. This looks good.
Okay, good. So no matter how many properties I put in A, I can look up any property on A extremely quickly. Order 1 operation. Doesn't matter how many properties I put in, I can look up C or D or B extremely fast. Now this is different than an array. If I do an array and that has values 1, 2, and 3, if I want to find the value of, the position of where 2 is in this array, so I have to go through every single value to say, okay, well, 2 is at position position 1, which is kind of confusing. Let me relabel this. So let's say I put in the strings X, Y, and Z. So I have my array B, that is the strings X, Y, and Z. If I want to find what position Y is in 1, I have to go through potentially every single value to find what I'm looking for and get that value. That's what's counted as O of n, right? Because that's linear. I have to linearly go through. If every item that gets added, I get a little bit longer, proportional to how long this array is. Hash maps are different. They have very fast lookup and insertion and removal for keys that which are these properties that you're adding and removing. So I want to talk briefly about how that works because I think it's one of the most fundamental things to understand if you're going to want to write fast code is what hash maps give you compared to like linear and this kind of stuff. So I'm going to talk about it, do my best to explain it. So if you have an array in physical memory, so if I did that B here is X, Y, and Z, I'll recreate that. So if I have B is equal to an array of X, Y, and Z, what that might create in physical memory is a data structure that looks like this. So here's physical memory, all kind of sloppily drawn. And I'll just say this is memory address 0, 1, 2, 3, 4, and so forth. Okay. What that might do is create, let's say it's going to create the X down here. It might say it's a string, and then it might just put the value of X. And then it might do the same thing for stir Y, and then stir Z. And if this is memory address 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What it might put in is something like this. This will be the object type for this array. And if this was just there might be an object type for this. There'll be a little bit of other information, but just the simplest form of this might be, it might just have memory address 7, memory address 9, and memory address 11. Right, so this is what an array looks like kind of in memory. There's different linked list forms of arrays. There's all different types of arrays. But kind of the simplest one is just sequential, and it's going to have a reference to, it's going to have a pointer, a number of the memory space of the value in that array. And when you insert something into an array, if I wanted to go through and find y, I'd have to like go through each of these memory addresses, then look up where, go to the memory address y, get this value, and either insert it or remove or do something like that. So that is how arrays kind of look like. Now I'm going to give you more of a pseudo approximation of how hash maps work. You can think of a hash map as in some ways an array of arrays. But the first thing to understand about a hash map is what a hashing function is. A hashing function, you guys might have heard of like something like MD5, other hashing functions that kind of take some set of data. I can give them like some kind of string like hello, and it might give me back, the hashing function might give me back a number, or in the case of MD5, it gives you like a 256 character string. No matter what you put in here, you get some character string. An arbitrary hashing function, I can pretty much give it any value here, and I can tell you how many bytes or what number I want to get back as some kind of seemingly random range. So I might want a hashing function that gives me a range. Anything I put in here, give me a number between 1 and 10, and try to keep it so that if well, maybe hello gives me the number 3, and maybe...
Hey, Justin, could you scoot that paper down and to the right? It's scooting up a little bit. Yeah, there you go.
So maybe maybe hello gives me 3, but maybe like hello A gives me 7 or something. Essentially, what it tries to do, it does its very best to do, is that even if your hello, like the next thing, like if it's sometimes easier to actually understand if I'm talking about numbers, but the next sequential value of whatever the string hello would be, where like maybe whatever comes after O is P. So if I had hello P, well, it doesn't map to 4. It might map to 1 or 6, or you can't. It tries to keep it kind of random. So even if you have a lot of sequential data, you don't get things mapping to the same number. It tries to very hard to be kind of almost random. Given a value here, what number over here it will map to. Although it's always deterministic. Like hello will always map to 3, but hello hel P might, you can't really determine where it maps to. That's an ideal hashing algorithm. But these hashing algorithms can happen very fast. They can take their data, run through it, and get a value very quickly. So what happens with an object, let's just do that example again, where I'm going to do var O equals a hash map. And then I'm going to do O dot A equals X, O dot B equals Y, and O dot C equals Z. Now what this sets up in memory, in physical memory, maybe I'll even get really creative here and use a different color. Well, I think I'll keep black for, well, no, I'll do this for the memory grid here. I'm going to turn this sideways so I can more easily draw a nice memory grid. many spots did I get myself? 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. I wish I'd given myself 10 because it would match what I was talking about earlier, but let's say our hashing algorithm is going to use 8 spots. So what happens is whenever you create a hash, it's going to create an array of a certain size. Now, JavaScript in reality will be really smart about how big of an array it creates. Well, let's say here it's going to create an array structure of 8 bytes. And what it's going to do is when you do O.A equals X, it's going to use the hashing algorithm on A, the property that you're setting. So it might do A, and then it's going to try to hash that into some value between 0 and 8. In this case, you'd use might be a 9. But let's say it would give, because there's 9 spaces. But let's say it's going to give A is going to hash to the number, let's say 5. Okay, so what it's going to do is at memory address 5, it's going to create a pointer to another array in memory somewhere else. So somewhere else there's kind of an array in memory, and I'm going to draw out this array this way. And what it's going to do in that array is put another. It's basically what it's going to do is put the value, the actual key value, A, and it's going to store the actual value 5. So you can think of it as like this points to some other array, and that other array has either other like kind of tuples in it that are the name of the property and the value of the property. So now B is going to be set. And let's say B hashes to 2. Well, what this is going to do in memory is create an array here. And it's going to say B, and it's going to put in Y. I don't know why I put 5 in here. That was my mistake. Sorry. It's putting the value. It's going to put X in here. So it puts the property and the value. Now let's say C is being written, and let's just say for some reason it happens that C hashes to 5. So it's going to put another item in this array in here, which is going to be C and Z. Now let's look at what happens when we want to look up the value of A. So someone wrote out, someone has now written out O.A. So we need to get this A property very, very fast. What'll happen is it's going to rehash A to memory address 5, and then it's going to start going through all the items in the array here to find the one whose key value is A, and then it's just going to return the actual value, and that's how you'll get O.A will give you X back. Let's say we were doing then O.B, or let's say we were doing O.C, reading O.C, it's going to do the same thing. It's going to hash C to the memory address. Why did I write 2? Sorry, I wrote 5, I meant 2. C is going to be hashed to memory space 2. So when we're reading O.C, we're going to go here and we're going to look through all of these objects to find the one whose property is C, and then we're going to return back Z. So this hashing is really fast. What you might be asking yourself is, well, what if you start getting a lot of these same values hashed to the same number? Well, what JavaScript will do, or Hashmap implementation will do, will rehash. It'll grow this list of placeholders. It'll grow it so that there's less chance of conflicts. So there'll be less items in here. What it does is always make sure that there's never more than, let's say, a certain number. There's never more than 10 items here. And if it's ever going to try to insert more than 10 items into one of these kind of secondary lists, it automatically rehashes. That way you can maintain that no matter what happens, I'm never going to have to check more than 10 items for a key value. And that's why it can say we're order 1. Even though it might have to do a lot of work to like go do the hash, then read a bunch of these different secondary values to figure out which one has your value, in the end, it's still constant time. Because if your number of properties gets large, well, you just rehash, and then you have less items in these secondary lists. I don't know if that makes sense to people. I can always take another crack at describing this, but I think understanding how hash maps work, and especially that they're order 1 lookup, is really, really important to writing good JavaScript code. And maybe in future lessons, I can show examples of people's code that I've found that will be looping through in a list and doing really expensive looping, order n a bunch of times, instead of where they could just be using order 1 lookup and making their application much faster. But this is the technology behind how that's the simple JavaScript object works.
To answer a question from the Gitter chat, from Omar Meki, wouldn't looking up a value still be big O of n here? And I think there's a clarification really quick. I know Justin was using the array bracket notation to the right, but that was mostly because of lack of drawing availability on this paper. But those are actually memory stacks. Correct me if I'm wrong, Justin.
Well, it's still an array-like structure, though. So it's not a true. I mean, you could use if you wanted to implement your own hash map. You could think of this as an array-like structure. Absolutely, there's a value here which might have, lower level it might be a tuple. It might just be like there's 2 bytes here and then there's 2 bytes here. One is the property value and the other is a pointer to the value. So this is still very array-like. But to answer the question, yes, looking up a value is still order n here, but n is only ever going to be a certain size. You might have to. It'll never allow the number of items here to, let's say, get over 10 items. Even if you have a billion properties, it'll never allow one of these secondary arrays to have more than 10 items in it. So that's why it's still order 1 lookup, because the time to look up is invariant with how many properties there are. It just keeps making this table bigger until nothing is larger than like 10 items or some specified number of items. It never has to check more than a few spots in here till it gets its value. So that's why it's still the lookup is still order 1, even if going on in here is order n, but n is always less than 10 or 5 or 100. It doesn't matter. And it never gets too big. So that's how that works. Cool. Any other questions? If not, then let me just quickly talk about what we're going to be doing next. Next week is comparisons. So if you've ever wondered about how triple equal or double equal operator works, that's what we're going to be going into next week. So Alexis and I will stick around for another like 10 minutes or so. If people have other questions about anything related to JavaScript, we can answer them. And now is a good time to ask questions that might need a whiteboard or something, just because I've got this all set up here. Yes. Because it keeps the I'm not exactly sure what your question is asking. But the question is, just to clarify, because n never gets too big, this will make our code run faster. Yes. Let me take maybe a step back even and talk about, kind of explain a little bit better what I was what I was actually talking about. When I talk about order of n, or like this O notation, there's certain algorithms that run, how to say, you don't want to say faster, but they run faster as the number of items gets very large, right? If you want to go through an array of items and find a value, that takes like the index of that value. When you use like array, if you use array index of, if you use index of in JavaScript, that is a order n. That we write that as it taking order n, because it might have to go through every single value in your array to find the value you're looking for to give you the index. Something like a sort, an array sort, that is going to be order n, and then the base 2 logarithm of n. So if you want to do a sort, it has to go through every single value in the array, and then also has to take the times essentially the base 2 logarithm of the number of items. So what that means is if I have like 1,000 items, or if I had like 1024 items, 2 to the 10 is 1024. So 1024 log 2 is 10. So if I wanted to sort an array of 1,024 items, that actually will take 10,240 steps to complete, because sorting takes n log n. So as the number of items get bigger, well, the base keeps growing a little bit, kind of slowly, but this gets worse than just finding the single index of course, because this grows much faster. Now there's other things that like, oh, if you're thinking about using React and do a diff, a difference of 2 arrays. Well, a difference of I should say what's another good example? A Levenstein or whatever distance. Let's say I had 2 strings, A, B, C, and I had A, C, B. There's algorithms that will take 2 strings and figure out what is the minimal number of changes I have to make to these 2 strings to make them the same. Those algorithms are n squared. So as this, if I had 1,000 characters, it would take a million. It would take kind of a million operations to figure that out, right? So these, when we talk about how long things take, there's certain algorithms to have certain kind of order of complexity values that are typically described by polynomials. There's some that are like 2 to the n that are very bad. These are things like the traveling salesman problem, where or if you want to figure out the fastest way in a from one point to another point in a connected graph that has like different values, like different lengths of time it takes to travel between each and every one of these things. If you want to figure the shortest path between 2 points, I'm pretty sure that's n squared. I'd have to double check if the values, if these have all different values, because you pretty much have to try every single combination. There's certain, greedy heuristics that lower this, and those are like that make it likely. So this is how Google can, Google will try to figure out your fastest way to wherever you're going, because it won't actually try every combination. It's smarter about which are the most likely combinations to work. So yes, typically when you use better algorithms to accomplish a problem that have a lower value, So order 1 is the best, right? That's the fastest. That means it's constant time. No matter how big your set gets, no matter how much data, no matter how many nodes, no matter how big your string, no matter how many anything, that always takes the same amount of time. And hash maps for insertion and removal and reading of values are order 1. So that's why I think it's really important to know how to use hash maps and kind of know what they represent. So that's why I did this little bonus session and got marker all over my hands. Any other questions? So it can be about anything related to front-end programming at this point. Otherwise, Alexis and I are just gonna hang out and stare at each other.
Just like every other day.
Yeah, we just wait for 7 days until these happen. We're just sitting in this room. That's all we do. Well, we can do until there's any other questions for now. We can do a meet the trainer. Alexis, you're in Dallas. Tell me about yourself.
I am in Dallas. Actually, maybe this is a good point to talk about our trainings. So I'm in Dallas, but I'm traveling around the globe. So like Justin said, if you're interested in trainings, if you happen to have any offshore teams, specifically in India, that are interested in training, Bitovi will be in India this summer, doing all this sorts of stuff, talking all things front end. So feel free to reach out to us via Twitter or email. For those that are following along, you may have joined us late. If you look in our Gitter chat, first off, if this is your first time joining us, we have a Gitter chat. Check out Gitter. Let me put the link. And actually, Justin, do you have the link? Looks like the. See if I can get a link out of this app. We are on the Bitovi channel. JS-training. Question from Sonji. I'll answer that in a second. JS-training. We have all the materials, slides, video, links to the Gitter chat particular to this training available at the Bitovi blog. That's blog.bitovi.com. So you can rehash all of this. Let me see here. Sonju question, how does this all relate to the DOM? Right now, we're basically going through the specifics with how JavaScript functions at a language. We're talking about all the basics of getting into JavaScript and, excuse me, any performance implications those things may incur. With regards to how this relates to the DOM, we are going to have quite a few weeks of specific DOM API, how we're manipulating, how you insert and remove elements from the DOM, how you listen for events on the DOM. So we're going to get into all that good stuff here coming up the next few weeks. So feel free to keep coming back every Wednesday.
Hey, I'm back.
Hey, I like the videos. All good. I like the videos. Are you guys going to give your viewers any practical work to do? Yes, Emmanuel Gittins. We are going to have exercises as we get deeper and deeper. Once we get past a lot of these introduction, today was obviously introduction to types and primitives. As we get deeper into the training, we are going to have exercises, so you can follow along with those as well.
Alexis, there were some questions in the questions app. Did you?
There were questions in the questions app. Let me bring that up. Oh, yes.
Yeah. So,
missed these. I apologize, Joe Blow. I see one question. When a pointer reference is removed in a delete scenario, but the physical memory still holds the value, however, the pointer is removed, when is physical memory cleaned up? Would you like to answer that, Justin? I believe that's the only question.
Yeah, so let me go back to the other video and try that then. Hold on one second. It's a really good question. Well, one, it's kind of unanswerable, but I'll do my best to end it. So can you see the page again?
Yep. Just a heads up, you're breaking up a little bit,
Okay.
but you're good.
Okay. I'll try to speak slowly then. So what happens is we can talk, maybe this is a little bit later to give a more complete answer, but you know how you have that variable, we had that data like, it was like me, and that was pointing at an object, and that was pointing at another object that was pointing at a string Justin. I'm just gonna write a string here because I kind of messed up my. Anyways, so this is the first, and this is the name. When we ran that code that deleted me.name, what that does is it just blows this away. It deletes this reference, right? So this object no longer has a name property. So this kind of stuff is just floating around in memory. So what JavaScript does for garbage collection, and this is how garbage collection works in general, is it works by reference counting. It first starts at this call object, and what it does is it says, okay, what does everything, if this is the window, it starts here and says, what does everything, what is this reference? So it follows, okay, me reference this object. So it marks this object as, I'm just gonna give a smiley face, as stays in memory, right? And if other things like in the window, like the document, like the actual document element might be an element in memory, or maybe you have some jQuery that is a jQuery function. It goes through everything here, and it basically marks it as not needing to be deleted. And then once everything is marked, it sees what isn't marked and knows if nothing else can actually talk to that object, then it knows it can actually delete the memory for everything here, because nothing else references that object. So garbage collection basically works by crawling through from the window, seeing what it can talk to, and if they can't get to some data, then it deletes it. But you can't actually ever know when that happens right now. It's not defined. It just disappears because your code actually can't reference it. So Sonjo? Hello, Sonjo. I don't know if I'm pronouncing your name right or wrong. If I'm butchering it, my mistake. How does this relate to the DOM? The DOM, as we talked about in the last presentation, let me go back to showing my face here. The DOM, as I talked about in my last presentation, is an interface for manipulating the HTML, but it's done for, you use JavaScript to change the DOMs. So if you want to listen to an event when someone clicks a button, or change a color of some text on the page, you use JavaScript to control that. So we think that this is why we're teaching JavaScript first, because you need to understand JavaScript if you're ever going to be able to manipulate the DOM correctly. Any other? Oh, the practical workflows. I think you answered that. It was cutting out, but practical not until a little bit later. Most of the stuff now is we are going to give some exercises to go through, but more of it is right now is like the theoretical JavaScript-y stuff for like probably the next couple weeks, 2 or 3 weeks, and then we will get into actually very practical work to do. Well, I think it's practical. Cool. Anything else? Oh, sweet. Thanks, Sonju. All right. Well, thanks everybody for coming. Oh, there we go. Another one. And in me.name, name is a property of me. Yes. Do you have a, John, do you have a more of a clarification for what you mean about that question? Or are you talking?
He was referring to our me example, one of the first slides we put up where we said name equals me.name. He was asking, first question was, is name a new variable? It is in that scenario. But name is also a property of the me object. So it is a little confusing if you're looking at that for the first time because the same name, well, the same label for the variable happens to be name in both places, but they are two independent properties.
Yeah, that's a good
question now.
Yeah, I can just show that slide again. Let's look at it. So, yeah, there's a name property and there's a name variable. So that's the difference.
We are on the left side, you notice in the JavaScript, we are using the shorthand, which maybe is part of the confusion. We're saying var me equals object, and then the comma is actually the same as saying var name equals me.name. So we could have said var twice, but
let me that's a good point. Let me write out like what this kind of breaks down to, and if you weren't using the shorthand. So you can think of it as writing it like this. Well, I'm going to say stir equals Justin, and then I'm going to create like the name object equals a new object, and what this is then doing is doing name object dot first equals stir, and then I'm going to create the, well, it's hard because, so this is this inner object that I'm creating right here, and then I could do the var me equals new object, and then I would do me.name equals name object. So this first kind of line is really doing all of this for you. It's a shorthand for creating the string and creating an inner object, which I'm calling name object, and assigning first to that string, and then creating the me object and assigning its name property to the name object. And then at the end of that, it's doing a var name equals me.name. Cool. Hopefully that answers it. Okay, everybody. I think this is where Alexis and I are going to call it and get back to work. Really appreciate everybody coming. Thanks for sharing your questions, and we'll see you guys next Wednesday.
Cool.
All right. Yep. See ya. All right. See you, Alexis.